Welcome everyone for this first SIPTA seminar of the academic year. So as usual, we give these seminars to give an overview of what happens in IP, sometimes inviting core IP people, sometimes inviting people that are familiar with IP and use imprecise probability in their work. And this is the case today because I'm very happy to welcome Dominique Guyonnet, who will give us a talk about application of uncertainty theory in the field of environmental risks. On the slide, you can also see the next seminar if you're interested. And usually we hand over to someone to make the scientific introduction and animation and question and answering. But since I know Dominique for quite some time now, I think almost since my thesis, I will allow myself to introduce Dominique and handle the question and answer. So Dominique is part of the French Geological Survey Institute. So he works a lot on risk analysis since quite a lot of time. So he has quite a lot of experience in exchanging with third parties, so either public institutions or industrials involved in industrial sites that has to be renovated. So basically the French Geological Survey, and Dominique is a core researcher in this institute, has the task to assess pollution level in sites and so on. So Dominique has a huge amounts of hands-on experience on risk analysis in concrete applications, and he has been using imprecise probabilities for quite some times, so more time that I've been a researcher actually, and which means a lot of experience in both fields. So I'm quite happy to welcome Dominique to speak to us about how he applies imprecise probability theories and imprecision IDs to his field of environmental risk. So Dominique, thank you for giving this talk, and I will now hand over the screen to you, and you're welcome to start whenever you want.
Thank you very much, Sébastien. Hello, everyone. So, yeah, my name is Dominique Guyonnet. I've been working at BRGM, the French Geological Survey, for quite some years. I should start with a disclaimer. You won't be learning anything today on the theory of imprecise probabilities. I'm not a mathematician, don't have that background. I'm a hydrogeologist by training. And so the notions I have in imprecise probability come from my interaction with specialists such as Didier Dubois, Hélène Fargier, and Sébastien and others. So hopefully the interest of this presentation for you will be to see applications in areas that are maybe exotic for your fields of work. Well, hopefully. So, I'll be doing a presentation on applications in the field of environmental risks. This is a sort of some content. I'll after an introduction, I'll say a few words about communicating on information theories with non-specialists. That's an important aspect of our work here. I'll give some examples that we either recent examples or some that are less recent in applications of imprecise probabilities to environmental problems. I'll talk again about communication and then propose some conclusions. So the material that I present today was essentially developed during the 1990s. My first encounter with my first encounter with these methods, well, it goes back to I was looking through my notes, and it goes back to a paper written by a guy called Bernard Combe, who was working at the Commission of European Communities in the 80s, and who was interested in these information theories, and he wrote a paper called Ensemble flou, Nombre flou, Incertitude dans les sciences de la Terre. And I turned out to be, well, at that time I was working in Switzerland. I didn't know Bernard Combe. But then when I came to BRGM in Orléans, well, he was a colleague of mine. So we exchanged on these methods, and that's how I got to be interested in imprecise probabilities. Well, in general, in alternative information theories for treating uncertainties in risk analysis. In the field that I'm interested in, it's essentially risks associated with contaminated soils. We have a general framework, which I should mention, which is what we call the source pathway receptor framework, because risk is a function of these different components. For there to be risk of damage on either on an ecosystem or on a human health, there needs to be a source of contamination. There needs to be a pathway which is going to bring these contaminants from the source to a receptor, and there needs to be a receptor who is vulnerable to the exposure to these contaminants at the source. If either of these components is absent, then there is no risk. And so you can treat risk by action at different levels at these different stages. And in what I'm going to present in the first application, we'll be interested in the source, treatment at the source, and we'll be looking at essentially the question, how clean is clean? Or what should the soil concentrations be so that there is minimal risk of damage at the receptor level? And when I started to get involved in these topics in the 90s, I read the literature, what was published in journals such as environmental engineering, and I was surprised to see that the practice was typically to postulate single probability distributions and to apply the well-known Monte Carlo method. And for example, I remember a specific study on risks associated with hydrocarbon contamination in soils, where there were about between 12 and 16 parameters that were described by single probability distributions that were essentially postulated, literally pulled out of a hat. And that bugged me, because it didn't seem satisfactory. How could you justify using single probability distributions when there was no data to substantiate those distributions? And so that's when I started to look into the question of alternative information theories, and I had the chance of being in direct contact with IRIT, in particular with Didier Dubois, who, if you know him, is someone who's very, very open-minded, always interested by new areas of research, and quite amazing. And so essentially the scientific question that we looked at specifically in our work with IRIT, it was the main scientific question that we addressed, was how do you combine both stochastic and epistemic uncertainty in the assessment of risk? Because the guiding, the fil rouge, the guiding principle of our research was to try to represent information in a manner which was consistent with the nature of the information that you have, instead of simply pulling single PDFs out of a hat simply for reasons of methodological commodity, comfort. And so that was we had a PhD with that was very successful with Cédric Baudry, who I believe it's still active in the area of imprecise probabilities. I don't know if he's a member of SIPTA, but he went after his PhD to apply these methods at INRAE in the fields of well, a whole load of different domains, very different from what I worked on, or from what he worked on in his PhD. I think one of the fields was the maturation of camembert cheese, which is quite original. And a notable result from that PhD and from the work that we did together was what I initially called the hybrid method, but which Cedric called in his PhD the joint propagation method, which allows one to jointly propagate both stochastic and epistemic uncertainties in the assessment of risk. And I'll come back to that. Just so that, well, this is, you are certainly very familiar with, but just so everyone's on board on what we're talking about, the classical Monte Carlo method in our area of application would be, well, you would have a risk model that would be a function of say a few parameters x, y, z, for which you can define a single probability density functions, probability distributions, and you sample them randomly, assuming independence, and you generate a different random number at each sampling, and you calculate your risk with this sample, and then you start again, and then you get n realizations, and you build a cumulative frequency diagram, and you can match a distribution on it if you want, but that's a result of the propagation that you can work with and compare it to thresholds. In our field area of environmental risk, we are often comparing estimated risk to threshold values, thresholds that are considered as acceptable values. For example, of soil concentrations, and I have an example after this that illustrates that. Whereas if you have the joint propagation method, let's say in the simplest case, one of our parameters is not, you don't have the information to represent it by a single probability distribution, but it's a simple min-max interval, for example, on Z, a min-max. Well, there you're going to sample randomly, like before, your PDFs, and then you're going to look at the min-max of your risk, considering all values in the interval, the possible values of Z. So the step adds computational effort in terms of finding optimizing over the interval values to find min and max, and you do that a number of times, so you end up with a random interval that you can classify using the belief functions of Dempster-Sheffer, in terms of an upper probability bound, plausibility, and a lower probability bound, belief, with which you are very familiar. Now, this method, well, of course, the Z could be a nested interval, a fuzzy number, and this type of application, there's a free application with coded in R on. This is the address where you can go into the library and get the application. So we've been applying such methods in environmental fields and been confronted with the difficulty of communicating on such information theories with non-specialists, because in fact in the environmental field it's not very common to address uncertainties in a rigorous manner. Typically in this field, in the field of environmental risks associated with soil pollutants, people are going to estimate risk with a model, and then because they know they should address uncertainty, and it's mentioned in legislation, what they're going to do is they're going to vary individually the parameters of their model between minimum and maximum values based on expert judgment. But they typically will do it about one by one. So it's more of a sensitivity analysis. And then when they vary it, they're going to obtain a min and max estimate that they'll compare to a threshold. So let's say the min and max interval that they obtained by their parameter variation is below the threshold, then they're happy, because the estimated risk is below the acceptable risk represented by this threshold. If it's above, well, they're not happy, but still they can decide that the risk is unacceptable. Problem arises when the threshold is somewhere in between, which is often the case. It's a problem because in that method, there is no discrimination of evidence within the estimated interval. And that's where these joint propagation methods are useful, because there you have a true discrimination of evidence, thanks to the belief functions of Denter-Scheffer, and you can work with these. I'm often confronted with the problem of explaining the difference between stochastic and epistemic uncertainties with non-experts, and because typically, the way I'll explain it, and this is an illustration that I made at a presentation, a conference organized by the French Environmental Agency, at which several researchers, including Didier Dubois, we had drafted a sort of synthesis on uncertainty treatment in the field of environmental risks, a synthesis for non-experts. And this is the illustration I used. Well, we were in an auditorium. Well, here it's a visio, so it doesn't really work. But if we imagine we're in an auditorium, you imagine you have a gas leak in this auditorium, and I'm in charge of performing a health risk assessment, seeing the consequences, assessing the consequences of this gas leak on health of people in the auditorium. And among the parameters I need for my assessment, there's body weight, because, well, the heavier you are, the bigger the dose that you can accept. And we assume two situations. First situation, that I possess a precise scale, and I have the opportunity of weighing each person in the auditorium. And in the second situation, I don't have a scale, I only have my expert judgment and the opportunity to just glance into the room. Well, in the first situation, where I'm measuring, I can report these results as a diagram of cumulative frequencies, and I can use that in my modeling, either directly, or I can fit a probability distribution on this data. And for example, if we were to pick a person in the auditorium randomly, well, we could say that we had a 50% chance that this person's weight was below 80 kilos. That's information that we can use. Yeah, I've already said that. In the situation B, where I'm only glancing in the room rapidly and using my expert judgment, well, I can see that well, it's not a congress of obese people or of anorexic people, so I can have an estimate of values outside which I would consider weights very unlikely, let's say 40, 120 kilos, and an interval. I could even express preferences within that interval, let's say 60, 90 kilos. And so this is typically information that is well suited to nested intervals, as illustrated below. And so, as you know, that this information represents, in fact, can be represented as a family of probability distributions. And so one must imagine all the possible distributions with within these upper and lower bounds, and the distribution that I described earlier is just one among a variety of possible distributions. And so this sort of illustration explains to non-specialists the difference between knowing and not knowing, and the fact that the information is the same. The data, the reality of body weights in that auditorium is the same, but it's our information regarding that data that is different. And it illustrates that these nested intervals are well suited to expert judgment. And that's an important message for, because often in this field, people talk about expert judgment, but they're not using the right tools to represent it. So this is a guiding principle that I mentioned earlier, that to represent information in a manner that is consistent with the nature of that information. This, we hope, should lead to more robust decisions in the field of environmental risk. So this is an illustration that there's a whole range of tools that are available that are suited to different levels of information, either poor level, I mean, complete ignorance, you know nothing, and that's a very rare situation. Usually, it's usually possible to at least define a min-max interval, all the way to very rich information, well, the richest being a constant. And there aren't so many examples of constant in our field or in physics, actually. I was thinking about that, and I think maybe the Max Planck constant would be an example. And it includes, of course, the nested intervals, probability boxes, and parametric probability families, with which you are probably familiar. That's a very useful tool that was, well, to my knowledge, developed by Cédric Baudry, and I'll come back to that. It's families of probability distributions where the epistemic uncertainty is on the modes of the distributions, on the average and the standard deviation, for example, which could be represented by intervals rather than precise values. Now, some example applications. I'll start with an application which is a recent one where I applied these imprecise probabilities to the soil health. Soils are vital component, vital for human health and animal health, because they deliver essential ecosystem services. For example, you see some services here: water purification, climate regulation by storage of carbon, provision of food, fiber and fuel, etc. And there's more and more realization of the importance of soils. And soils are under threat by various hazards, such as erosion, contamination, soil sealing, salinization, especially with the droughts. Well, you have seawater, which is penetrating further and further inland and salinizing cropland. According to the Joint Research Center of the European Commission, around 65% of land in Europe is affected by some sort of soil degradation, whether it be contamination, sealing, or salinization. In some cases, soils require remediation, treatment, and in that case, environmental authorities will define an objective. How clean is clean? What should, after remediation, what should the soil concentration be? And typically, these values, which are threshold values, are crisp, they're precise values. For example, arsenic concentrations in a given soil should be lower than, for example, 50 milligrams per kilo. That's a typical value. And uncertainty is often taken into account in this context by accepting that a certain proportion of concentrations after treatment are above the threshold. And what that proportion is depends on the environmental authority. Typically, because they define a crisp, precise threshold, well, you will have, after remediation, you'll have values that are below the threshold, but they'll account for uncertainty by accepting that a certain number of values are above the threshold, but it's not very, it's ad hoc. How far above? Factor 2, factor 3, on which basis? So it's not a conservative approach. It's not a very rigorous approach. And what we have proposed is to take into account epistemic uncertainties in the definition of these thresholds, and to define the risk-based objectives as intervals rather than crisp values. And the advantage of that is that if you have an interval, well, you have an upper safeguard that constrains control values, monitoring values after the remediation. So it's these monitoring is performed once the remediation has been implemented. They will take samples of soil and verify that the concentrations in the soil are below the specified threshold. So if you have a threshold as an interval, then you mustn't go above this upper limit, and that's a plus compared to this to precise, crisp thresholds. So how do we go about defining such an interval? Well, the proposed approach is to use the belief functions of Dempster-Sheffer and to estimate a lower soil limit such that we are certain, that's belief, that the risk is below a threshold. And typically in our areas, the risk threshold will be 10 to the minus 5. That's a expected cancer, a level of expected cancer associated with this contamination. So that would mean that on average, 1 in 100,000 persons exposed to this contaminated soil would develop a cancer. So it's an accepted level of risk. So we estimate a lower soil concentration limit such that we are certain, using the belief function, to be below the threshold at least 90% confidence level. So here, for belief, we're considering all the unfavorable parameter values, values of parameters in our risk model. And the upper soil limit would be defined by the plausibility function, so that we define the upper soil concentration such that it remains plausible that the risk is below the threshold at 90% confidence, considering all favorable parameter value combinations. So we have a min and a max using the plausibility and belief. So sea soil min is a very conservative limit because it considers all the unfavorable pessimistic parameter value combinations. So we have a high level of certainty with sea soil min that we're below the threshold. And sea soil max is a non-conservative limit, considering all the favorable value combinations. But with sea soil max, it still remains highly plausible at a plausibility of 90%, that risk is lower than the threshold. So that's our proposed method. And this is an application to arsenic contaminated soils in the northeast of France. It's an old steel industry where we have several million cubic meters of slag. And we were in charge of assessing risk associated with these materials. And the assessment included characterization, speciation of arsenic and lead in the samples, characterization of bioaccessibility. Bioaccessibility is the how much lead in the soil actually, if you're exposed, how much actually gets into your system. So it's lower than the total concentration in the soil. And all this, we performed quantitative risk evaluation. And the risk model considers, well, estimates an individual excess risk, which will be compared to that 10 to the minus 5 value that I showed you. And it considers a dose of exposure, a dose absorbed following exposure, and a unit excess risk, which is a risk of excess cancer per unit dose. And the dose is a function of a number of parameters, soil ingestion. I'm not going to go through this. The bioaccessibility I mentioned, exposure frequency, duration, body weight that we saw earlier, averaging time, etc. And these parameters, we need to represent them using the data that we have. In this model, we have constants. Well, we're varying sea soil as a constant to adjust to the level of risk, as I illustrated. We're considering a child exposed to these contaminated soils. And so we take 6 years. This is a standard methodology in the health risk assessment. The unit excess risk is defined also. We have one probability distribution based on statistical data that we have. Body weight with an average of 15.5 kilos and standard deviation 5.4 kilos. This is the reference. And the other parameters are possibility distributions based on scarce data or expert opinion. For bioaccessibility, we define the possibility distribution by fitting the resulting family of probability distributions on the measured data. So this is the bioaccessibility in terms of possibility and associated probability, cumulative probability distributions. So you see we encompass the scarce measured data. For other parameters such as soil ingestion, exposure frequency, etc., we're using essentially literature data and expert judgment. And so we propagate this information in the risk model using the independent random set, the IRS model of Baudry et al. And we obtain the sea soil min and sea soil max, such that for sea soil min, if we have, as long as sea soil is less than 61 milligrams per kilo, we guarantee that we have at least a belief of 90% of being below the excess risk of 10 to the minus 5. And for sea soil max, if we're less than 739 milligrams per kilo, we have at least a plausibility of 90% of being below the 10 to the minus 5. So in terms of application in post-remediation context, we would say that the monitoring values after remediation should yield values that are lower than 61 milligrams per kilo, while a certain number, and that's to be defined, typically it's on the order of 10%, could exceed this value, but should always remain lower than 739 milligrams per kilo. So the difference between the classical precise, crisp approach is, on the one hand, we're trying to be more faithful to the information that we have, but we also have an upper limit, which is risk-based, this 739 milligrams per kilo. So that's the first example I could illustrate. The second example, I'm really going to go through it very fast because otherwise I'll probably run out of time. It's a risk of leakage from what we call heap leaching facilities, which are used to treat mining ore by passing fluids through the ore heap. They excavate the ore, and you pass a fluid, for example, a cyanide-rich fluid in the case of gold ore, through the heap, collect the fluids, and then recover the gold or the metal from these fluids. So here you see the ore heap here. You see they have a storage pond for their fluid. They pass the fluid through the heap, recover, so it percolates through the heap. You recover it at the bottom. You get what they call a pregnant solution, and you treat this pregnant solution to get the metal out. So obviously you need to collect all this fluid. So you need very impermeable barriers at the bottom of your ore heap. And that's where there's some risk, because these permeable barriers, sometimes there are defaults in them. This shows you that the scale of the ore heap, the heap leaching facility. This is the ore. This is a little person. So it's enormous scales. You can have different types of solutions that I've said. And so we performed risk assessment for design purposes. This is a schematic which shows you the multi-barrier system. You have drains, and you have high density geomembranes, and then you have your foundation layer. But you can have there may be defaults in the geomembrane, as I'll be illustrating. This is geomembranes that are stored, typically unrolled to create the barrier. Here you see making the bottom barrier with these high density polyethylene geomembranes, and they have to be welded between them to guarantee that it's impermeable over the entire sheet. This again gives you an idea of the scale of these facilities, which is 65 hectares, 100 meters of ore height. It's really enormous. This is the bottom drainage layer with sand. The geomembrane is below this. This is on top of the heap where they're injecting the fluids. These are geomembrane typical defaults in the geomembrane, where here you have the welds which haven't been done properly, and here the fluid can pass through. This is a puncture made by a sharp object. This is really a big hole, because the membrane was the foundation layer has sharp. They have stones here, silex element, and sometimes they roll with lorries over it, and it punctures a geomembrane. So we have a leakage model that is a function of that calculates a leakage rate, a function of a number of defaults per hectare, default surface area, and various parameters. And again, you go through characterizing and describing these parameters as best you can with the information that you have. Sometimes you have distributions, and sometimes you have scarce information, expert judgment, and so you're going to use possibility distributions, and then you propagate this through your model and obtain an imprecise probability of being below a certain leakage value that will be defined by the environmental authority. You can also compare such simulations to measured data. These data this data I'll be showing is measured in what we call double barrier systems, where you have a first drain and a secondary drain. And so in the secondary drain, you collect what has leaked through the defaults in the first drain, and you get values that typically within the 500 to 1,000 liters per day per hectare, which compares quite well with the simulated values. So this was a second example. The third example I'll very briefly present is the interpolation of what we call SIC data. SIC stands for scarce, imprecise, and clustered. And this work is performed as part of an ongoing French research agency INR project called Houses, in which Sébastien is participating. And essentially, why we're doing this is because we're interested in drawing maps. And this is very common in our field of work, where we draw maps, for example, of here a map of arsenic concentration in French soils. This is data collected by INRAE, which is the French Agronomy Institute, where you see a map of France and values of concentrations of arsenic in this on this map, calculated based on individual point data at various locations. Typically, in this case, it's locations on a grid of measurement every 16 kilometers. It's a 16-kilometer grid. And so such a map is obtained by interpolation, typically using methods such as geostatistics, using the Kriging method. So this is a nice map with quite rich data. Oftentimes, you don't have rich data, but you have sparse data or sick data, sparse, incomplete, and clustered. You might have lots of data at some points, at some areas, and very low, scarce data in others. And in that case, geostatistical methods reach their limits. This is an example that a colleague passed on to me. The dates goes back to 1975, called Relative Effectiveness of Geologists and Computers in Mapping Potential Hydrocarbon Exploration Targets, where they had the original data, which was 13 values of sand thicknesses in borehole cores. And this is what you obtain by direct manual triangulation. And this was obtained by a first geologist who assumed a certain model of a sand deposit, a fluviatile deposit, and then another geologist who had another model in mind. And so you get something completely different. And so this illustrates the ambiguity of interpolation when you have very scarce data. And this is what is being explored with various partners, including Yazik Irit and the Paris School of Mines. And it's led by BRGM. This shows that illustrates we're testing different algorithms to interpolate. This shows 6 algorithms on the same data set, a nearest neighbor algorithm, inverse distance weighting, quantile random forest, inequality Kriging, experimental probabilistic hypersurface, and belief map. So several of these methods exploit imprecise probability approaches. And there's a first publication of a review study performed as part of another project in Journal of Geochemical Exploration. Finally, communicating on imprecise probabilities. Well, as I said, it's quite uncommon in the field of environmental risk engineering to use actually crisp probabilities of exceeding acceptance thresholds, let alone imprecise probabilities. So imprecise probabilities really has a long way to go in terms of acceptance in this field. Maybe others, I would assume also. And one tool that we've used, for example, if I go back to the simulation of leakage through the bottom barrier of a heap leakage facility, we've proposed in a paper with Didier to define a confidence index as a weighted average of plausibility and belief, borrowing from work by Hurwitz in the 50s. So at each level of probability, we'd have a weighted average and using a parameter alpha, which would be arbitrary, but to a certain extent arbitrary. we would give more weight, we would choose alpha such that we give more weight to the pessimistic estimator, which is belief, rather than to the optimistic estimator, which is plausibility. Here's the result for a alpha value of 1/3, so where we're giving 2/3 of weight to belief and 1/3 to plausibility. And this we could use as a unique indicator of the evidence of being below a threshold. This is an alternative that we propose. We can also aggregate plausibility and belief into simple indicators of confidence for communication. And I strongly advocate using methods looking to the weather forecasting community in terms of experience in communicating on uncertainty with the general public. They have much more experience than any other field I'm aware of, and I think we could learn from this community. A few conclusions. Uncertainty is an unavoidable aspect of risk-based contaminated land management and soil remediation. When addressing uncertainty, we advocate to first look at the information, then choose a mathematical framework for representing and propagating this information in the estimation of risk, rather than going straight into a mathematical framework for reasons of commodity. We think it's important to account for uncertainty of epistemic origin, to convey to decision makers the range of possible outcomes, and it may also highlight the need for additional data collection. Whereas if we just postulate single probability distributions, well, there's no way of distinguishing in the variance of the output what is resulting from true randomness and versus what comes from subjective probability judgment. And well, obviously there's a long way to go before imprecise probabilities are really part of the decision-making process in the area of environmental risk. It'll take some time. Thank you for your attention.